Okay, good. I think I can see your slides.
Okay. Can you see my cursor?
Yes, I can also see your cursor.
That's good. I didn't really use Google Meet to present, so
Yeah, that's fine. It seems like everything works perfectly. So
that's good.
yeah. So Binrui, should we start now or?
Yes, I think go ahead.
Okay, good. So hi everyone. So this is today's condensed matter seminar, and it's our pleasure to have Yuping Lin to give a talk about his recent work. I think it will be a very interesting topic. And here I'll just give a brief introduction about Yuping. So Yuping graduated from National Taiwan University since 2014. And then he started his master thesis working with Professor Ginzburg-Landau in some work related to tensor networks on some Ising chain and some disorder physics. And since then, I know Yuping, and he basically worked on various different subjects. And after he graduated from Professor Injagao's group, he joined University of Colorado Boulder and worked with Rahul Nankishore, who is an pioneer in many-body localization and quantum dynamics, and also experts in some of the famous renormalization group techniques that is developed in graphene system. So at that point, Yuping make a twist about the research direction and also work a lot on the study of renormalization group and the study of topological band theories and related mathematical structure behind these topological bands. So I think today I'll just leave the time for Yuping to introduce his recent work. Basically, is his calculation on some of the very interesting materials that people get a lot of attention about. Is basically these kagome metals, and that's welcome him and um, um, I don't know, maybe give a virtual pause. Okay, so let's start.
Yeah, so thanks to Yuping for the introduction, and thanks to everyone who joined my talk here. So I'm Yuping from Colorado Boulder, and today I'm really glad to give a talk again at NTHU. And I guess maybe some of you still have still remember a little bit about what I talked last time. And my talk this time will be a little bit related to what I have mentioned last time. So today I'm going to talk about the Van Hove singularity on the hexagonal lattices. In particular, I will focus on the possible complex charge density waves that could realize a Haldane-model phase diagram. And I'll also show that this kind of complex charge density waves may be relevant for the recently observed kagome metals. So let me first present my acknowledgement first to my advisor Rahul at Boulder, and also to the condensed matter theory group at Boulder. So this was taken in Winterler. I think Yuping is also familiar with that. So here is an outline to my talk today. First, I will give a background introduction to what I'm going to talk about today. I'll start with the introduction to some of the hexagonal lattice system, and later focus on the Van Hove singularity. And also I'll present some real materials that are related. Then I'll start the introduction to my research. First, I'll introduce to you about the low energy theory at the Van Hove singularity. And then I will tell you about the charge density waves that could realize. Then I'll show that this kind of complex charge density waves can host a rich Haldane-model phase diagram where you can find the trivial and Chern insulators. Then I'll show that this kind of complex charge density waves may explain the recently observed CDWs in the kagome metals. And at the end, I'll end up with a summary. So first, let me give a background introduction to the hexagonal lattices. So, maybe you have already been familiar with some of the hexagonal lattice systems. And by hexagonal lattice, I refer to the triangular, honeycomb, and the kagome lattices. So I believe that the most familiar example for you is the graphene with the honeycomb lattice. And also there has been other, for example, spin liquid systems, which were proposed in the Kitaev model on the honeycomb lattice, or the spin models on the triangular and kagome lattices. But today I'm going to focus mainly on the itinerant electron systems instead of those strongly correlated systems. So first, let me take a warm up of the hexagonal lattice with the first example of graphene. So graphene is a honeycomb lattice system, as you can see from the lattice figure here. So we can think of the honeycomb lattice as composed by a two-side unit cell, where we refer to the two sides, sublattice sides, as A and B. And if we consider it in this way, we can think of it as a triangular lattice, where the lattice sides are the two sublattice side unit cell. And because it has a triangular lattice, Bravais lattice, in the momentum space, we will have a hexagonal Brillouin zone. And we will refer to the zone center as gamma, zone corner as K, and the edge center as M. So with the lattice structure, we could try to calculate the band structure of it in the momentum space. So to do this, we can think of graphene as having a pseudo-spin 1/2, which corresponds to the two sublattice sides. And the Hamiltonian will take a 2x2 form, and it could be thought of as a pseudo-spin in a pseudo field, which takes this form. It is a coupling between an h of k inner product with a sigma, where sigma is the Pauli matrix. And you can think of it as an analogy of the spin 1/2 in the magnetic field. So the band structure looks like this. We have a particle band and a Hove band, where the 2 degrees of freedom correspond to the two sublattices. And also, there is a particle Hove symmetry. That is, if we look at the Hove band, it could be obtained by just reversing the sign of the particle band. And a particularly interesting point is at the charge neutrality, where you can see that there are two inequivalent values at the k and k prime points, where k prime is just negative k. And if we look closer to the two values, and with an infinitesimal q as the momentum deviation from plus minus k, we find that the h1 and h2 will become linear in the momentum deviation q. Meanwhile, the third component will be nearly a constant, and the low energy dispersion will look like this. So this will be linear if the mass vanishes, and it will be quadratic if the mass is finite, which correspond to masses and massive conditions. And we can understand it further by considering the symmetry of graphene, and it will turn out that the third component should vanish. So first, let us look at the inversion symmetry. So by inversion, we can think of it as reversing A and B sublattice sides. It means that in terms of the Hamiltonian, we can think of it as a transformation, a unitary transformation with the off diagonal sigma 1. And under inversion, we are mapping k to negative k, so the Hamiltonian are related. And under inversion, it is required that the third component has an opposite sign between k and minus k. Meanwhile, there is also a time reversal symmetry, which corresponds to the complex conjugate of the Hamiltonian. And because the momentum is also reversed, that is, k is mapped to negative k under time reversal, we're also relating the Hamiltonian at Kn minus K. And under time reversal, the third component should be equal for Kn minus K. So by combining both inversion and time reversal, we find that the third component at K should be both negative and positive equal to the third component at negative K. So it requires that the third component should vanish. And if we look at the values, we'll find that if we have both inversion and time reversal symmetries, we will have the mass to be either negative or plus equal between the two values. And it also means that we should have massless condition, which correspond to the vanishing of the third component. And this means that the graphing will have direct points at Km minus K, or you can say Km minus K, with a linear dispersion. And this makes the graphene as the kind of direct semimetal in two dimension. So it turns out that there are some interesting topology from the direct points, which could arise from either the gapless and gap or the gap condition. So first, we could try to map the Hamiltonian onto a Bloch sphere, where we can define a unit vector as the direction of the Schudo's field, and then it could go around the unit sphere. And the mapping of the Hamiltonian to the Bloch sphere could be thought of as wrapping the Brillouin zone onto the Bloch sphere, and the wrapping should correspond to a zero or finite integer. If we have both inversion and time reversal, we know that it is required to have a vanishing third component. So the unit vector should always lie on the equator. It means that if we look at the plus and minus K with the direct point, if we go around them, we will have a phase winding, which is equal to spin 1/2 times plus or minus 2 pi around the equator, and it will correspond to plus or minus pi. We can now try to break the symmetries to gap out the direct points. And if we break the inversion, the time reversal symmetry enforces the same sign between the third component at K and minus K. And we know that the plus minus K's are the points in the Brillouin zone where the first and second components vanish. So on the Bloch sphere, they should correspond to the north or south poles. If we have time reversal but no inversion, both of the poles will lie on the north pole. And it means that if we go around the Brillouin zone, we will not have a finite wrapping. The wrapping onto the Bloch sphere will be 0. However, if we break the time reversal symmetry, the third components at K and minus K are related by a minus sign. It means that K and minus K locate at opposite poles on the Bloch sphere. And if we go around the whole Brillouin zone, we're wrapping the Bloch sphere with a wrapping number plus or minus 1. So the wrapping number could actually be identified with the Chern number of the band. And the Chern number can be thought of as a quantized geometric phase when we go around the Brillouin zone, and it is an integer. An important physical realization of the Chern number is that if we apply an electric field in the x direction, there will be a response of the current in the y direction, and this kind of whole conductivity will be quantized, and the quantization is defined by the Chern number. And this will give the non-trivial topology of the band structure. So there is a proposed realization of this kind of topologies, which was posted by Haldane back in 1988. So this is a figure for the graphene honeycomb lattice. If we only have the honeycomb lattice without any other additional things, we know that we have both inversion and time reversal symmetries. And if we look at the band structure, we'll have a pair of null points, which defines it as a direct semimetal. We can now try to break the symmetries. So first, let us try to break the inversion symmetry, which could be realized by introducing the on-site potential at A and B with an opposite sign. And if we make this kind of sublattice imbalance, we're breaking the inversion. And as we saw in the previous slide, it could lead to an insulator with Chern number 0, and so it is a trivial insulator. Meanwhile, if we break the time reversal symmetry, we could try to realize it by introducing some magnetic fluxes on the honeycomb lattice. For example, we could introduce a magnetic flux A in this triangle and the other triangles, and we could introduce another magnetic field B in this triangle and other analogous triangles. So what is the result of this kind of magnetic fluxes? First, let us look at the second neighbor hopping, which forms a loop around the 3 A sublattice sites. We can see that this triangle encloses 3 B fluxes. And with this kind of finite magnetic flux, it turns out that the second neighbor hopping will realize a current loop. So we will have spontaneous currents between the A sublattice sites and similarly between B sublattice sites. However, if we look at the whole unit cell, we find that we have 6A and 6B. And because we require A is equal to negative B, the net flux through a unit cell will vanish. It means that we do not really have an external field. So we're breaking the time reversal symmetry without an external magnetic field, and it will gap out the system with a finite Chern number, so it is a Chern insulator. You can think of it as a quantum Hall effect, but without an external magnetic field, so it is also known as a quantum anomalous Hall insulator. So we can now look at the phase diagram here. First, if we preserve both inversion and time reversal symmetries, which correspond to 0 on-site potential and also some real condition for the phase, that is 0 or pi, we're having the Dirac semimetal. And this Dirac semimetal will serve as a critical point between the Chern and trivial insulators. If we introduce the on-site potential, it will go into a trivial insulator. If we introduce a complex phase which corresponds to the current, it will go into a Chern insulator. However, if we look broader in the whole phase diagram, we generally don't have either inversion or time reversal symmetry. And there are some continuous phase boundaries which are not direct semimetals. So what are they? First, we can think carefully about it, that if we don't have inversion or time reversal symmetry, the energies, the band structures at k and minus k don't have to be symmetric. So we do not have fermion doubling theory here. So it turns out that if we look at the phase boundary, it should be gapless. So we should at least have one gapless point. And without inversion and time reversal symmetry, we are not required to have a pair of gapless points. We can have just only one. And if we look at the band structure, there is indeed only one gapless point. So it is a single-Dirac-point semimetal. And we have this kind of rich phase diagram for the Haldane-model, but it is a pity that the Haldane-model hasn't really been realized in the solid-state materials, although it has been realized instead in the ultra-cold atomic systems. So we may still want to have it in the solid-state materials. And to think about it, a potential answer is to introduce the interactions and see if there are some effective theories that are analogous to the Hotend model. So now let us try to introduce the interactions to the solid-state systems, or you can say to the graphene. So to introduce interaction, we know that we need to have some number of fermion modes on the Fermi surface so that they could interact. This means that the density of states at the Fermi surface will be important. If we look at the Dirac point, we'll find that the linear dispersion means that the Fermi surface vanishes at the Dirac point. And more rigorously, you can say that the density of states vanishes as the energy goes to zero, that is, as we approach the direct point. It means that we're having a vanishing interaction effects. So we should look at a finite doping where we could have a finite density of states. And a particularly interesting point are the sail points at the endpoint, where if we are having a small momentum deviation, then the energy deviation from the sail point will be q squared minus q squared, where you can see that along one direction you have a negative curvature, and along another direction we have a positive curvature. So this kind of sail point defines a Van Hove singularity in the density of states. That is, it will become logarithmic divergent as we approach the sail point energy. And you can see it from the density of states here, that there is indeed a log divergence. So if we have a log divergence in the density of states, it means that there is a strong amplification to the interaction, so that it may be easier to observe the correlative phases that come from the interaction between electrons. So we'll focus particularly on this kind of Van Hove singularity and see what kind of correlative phase there could be.
Can I ask a quick question?
Yeah, sure.
So, so the argument that at the finite, like when the epsilon goes to zero, that's when you reach the Dirac points, the density of state vanishes. But because of density of states vanishes, doesn't that mean like the screening effect will also be suppressed? In that sense, the interaction effect is not really, it is like not so trivial to drop it. So
yeah, that's true. Like if we have a strong, it is in the weak coupling limit actually. Yeah, so if we have a stronger coupling indeed, there might be some correlative phases that are not screened out. So there are some other kind of correlative phases. But if we focus on the weak coupling limit, then we can think of it as effectively non-interacting.
I see. So so the statement is that assuming that the coupling is not too strong, then the perturbative argument will suggest that the vanishing density of states actually leads to weakly correlated physics. But as there's a threshold that once the interaction is too strong, then the screening effect will kick, the suppression of screening effect will kicks in. Then the theory will become a basically strong coupling theory. So you are working in the weak coupling region, and ask if you try to dope your system or such that the chemical potential is sitting at the settle point of the band structure. Then what's the effect of Van Hove singularity at the weak coupling scheme?
Yeah, that's true.
Okay. Okay, thank you.
That's a good question. Thank you. So so let me now look further into the Fermiology, that is the structural Fermi surface at the Van Hove singularity. And it turns out that at the Van Hove singularity, the Fermiology is universal on the triangular honeycomb and kagome lattices. So the three lattices will have this kind of band structures. We can see that for triangular lattice, there is a Van Hove singularity. And for the honeycomb and kagome lattices, there are two. So if we look at the hexagonal Brillouin zone, we'll find that the Fermi surface, which is the red line, forms a hexagon, where the corners sit at the sail point on the edge center, and the sail points are related by a finite momentum, by three finite momenta Q1, Q2, Q3. Okay. So maybe I should explain further into the band structure here. So for a triangular lattice, we only have one side in each triangular, in the unit cell of one triangular lattice. So there is only one band. And for graphene, we have two sublattice sides. And for kagome lattice, we have three sublattice sides. So we will have 2 and 3 bands for these two lattices. And it turns out that there are two finitely dispersive bands in these two lattices. So there are two Van Hove singularities here. So if we introduce the interaction, the singularity at the Fermiology will amplify the interaction effect. So what are the singularities at the Van Hove Fermiology? First, we have the Van Hove singularity of the density of states. Secondly, we have the nesting, which occur at the Q1, Q2, Q3. That is, if we look at a point near the Fermi surface here, and we shift it with a finite momentum q, we'll find that they are opposite to each other, and this occur along the Fermi surface. So combining these two singularities, we will have log-squared divergences, which is scaled with the temperature. And if we introduce the electronic repulsion, it turns out that it will enhance the instabilities. So the next question is, what kind of instabilities are there?
Sorry. I want to ask about the divergence of what?
Of the one loop contributions.
Of some observable, right?
Yeah. You can think of it as susceptibility to the fermion bilinear.
I see. So it's a 2-point function divergence.
4-point function.
Sorry, 4-point function. 4 points. Current.
Yeah. So it's a 2-particle function, but a 4-point function. Yes.
Yeah, I understand. Okay, thank you.
So first, we could have superconductivity, which occur when we have a finite condensate of Couper pair at -k and k, and both of them are holes or particles. Meanwhile, we could have the density waves, which is the coupling between a particle at a momentum and a hole at another momentum, which are related by a finite q. And if we can have either a condensate in the charge sector or the spin sector, it means that we can have either the charge density wave or the spin density wave. So because the momenta are equivalent to the cell point momenta, that will be half of the reciprocal lattice vector. It means that the momentum q's are commensurate to the lattice. And because our wave vectors are halved, our periodicity in the lattice will be twice. For example, our original periodicity is one lattice vector, and now it will be twice to 2 lattice vectors. It means that our unit cell will not be enlarged into a 2x2 structure. Meanwhile, in the momentum space, because our wave vector scale is halved, it will become a 1/2 times 1/2 reduced Brillouin zone. And we indicate it by the brown hexagonal region here. So we might want to understand further about what kind of density waves there could be. So we can think of the density waves as the density modulations at finite momentum q. For example, if we have a charge density wave, we could have a density modulation like larger, smaller, larger along a direction. And if it is spin, then it could be up, down, up in this as with a two lattice side periodicity. So if we can distinguish them further into real and imaginary channels, if it is a real density wave, we know that a real component of the side dagger side is the density, and it will correspond to the side or bound density modulation of charge or spin. Meanwhile, if it is imaginary, we know that if we have an imaginary component of the side dagger side, for example, in the Schrödinger wave function theory, it will correspond to the current of the particles. It means that we might have a current flowing in this direction, but a current flowing in the opposite direction when we go to another bond. And this will be referred to as the current density modulation. So we have identified the possible instabilities at the Van Hove singularity. So what are the leading instabilities that could really arise? Let us first look at the
Can I ask a quick question?
Yeah, sure.
So I'm a little bit lost about the choice of the Qs. So at the part about the density wave, you said that the density wave is defined to be this vector m, and I think my question is, in principle, the density wave could have various different kind of, you know, Q vectors, even non-incommensurate one. So how did you choose that it is 2Q?
So we are looking at the weak coupling limit. So the log square divergence only occur when we have the nesting at these Qs. So these are the leading divergence in the one loop contribution, as Boyle has just asked. So we will want to focus on this momenta Q1, Q2, Q3, where the one loop divergence will be the strongest.
I see. So it's based on some already some theoretical calculations suggest that at least like at one loop level, the most important divergence are basically this 2Q contribution. I see. I see. Okay.
Actually, I'm going to show that in the next slide.
Okay, thank you.
Yeah, so this is what Ibn has just mentioned about. So we want to know what are the correlative phases that are the leading instability. So for the graphene and triangular lattice, we can think of it as procedure like this. First, we have the nesting at the Van Hove singularity, and the nesting could lead to some one-loop leading divergence, which could trigger the spin fluctuations, which have a finite momenta Q1, Q2, Q3. And if we go further into like lower temperature, it will trigger the superconductivity. The Coulomb pairs may be mediated by some kind of antiferromagnetic spin fluctuation because the spin fluctuation is at finite momenta. So here is a phase diagram which could be eligible for graphene and triangular lattice. If we look at the Van Hove singularity, we can look at the scale of the phase diagram, which is analogous to the critical temperature. We'll see that near the Van Hove singularity, there is a competition between the chiral D plus ID superconductivity and the charge density, the spin density wave. And away from it, will be some other superconductivity. So it turns out that under a renormalization group analysis that Rahul did in 2012, the chiral superconductivity will be the universal leading instability. And the chiral, because it is chiral, it breaks the time reversal symmetry. So how does it break it? Actually, it breaks it by having a Coulomb pair which winds for plus or minus 4 pi in terms of its phase when we go around the Fermi surface. So this kind of phase winding breaks the time reversal symmetry. And because it is like plus or minus 4 pi, it corresponds to the D wave form factor. Meanwhile, we could also have the real spin density waves, which are the next leading instability. And it will be the 3Q order ground state. That is, the ground state will have simultaneous formation of orders at Q1, Q2, and Q3. So in terms of different spin structures, we could have different ground states. The first kind of them is the uniaxial order, where the spin at the Q1, Q2, Q3 point along the same direction. In this way, if we look at the lattice and look at a unit cell, we'll see that there is a 3 -1, -1, -1 structure. And if we look at the band structure, it will realize a half metal, where it is gap only for a spin up band and it is gapless for the spin down band. Meanwhile, we could also have the spins pointing in different directions for the Q1, Q2, and Q3. So you can see on the lattice that there are some spin structures along different directions. And in this way, it will realize a Chern insulator. So we have a rich phase diagram already for graphene and triangular lattice. The problem is that for these two lattice systems, the doping to Van Hove singularity is at the electron volt scale. And if we think of this scale in terms of the temperature, it will be analogous to the 10,000 Kelvin. And because it is a really high energy scale, it is really hard to achieve it. So we may try to look at some other systems. So the next case we're going to look at is the kagome lattice. So for kagome lattice, we have 3 bands where one of them is flat. And there are 2 Van Hove singularities that occur on the 2 finitely dispersing bands. It turns out that the 2 Van Hove singularities have different cell point sublattice structures. For the upper bands, we'll see that each of the cell point only enjoy the contribution from one sublattice site. Like this cell point has it from A sublattice site, and this from B, and this from C. Meanwhile, for the lower Van Hove singularity, each cell point will have 2 sublattice site contribution. So this will lead to different types of instabilities. First, let us look at the particle band, where there is only one sublattice site contribution at each cell point. If we introduce the on-site repulsion, where A is only coupled to A, B is only coupled to B, and C is only coupled to C, we'll see that the cell points are not coupled to one another. And if we introduce the on-site repulsion, the leading instability at low temperature will be either ferro or anti-ferromagnetism, which is the side dagger site at the same cell point, and it will be a zero momentum instability. However, if we introduce the first neighbor repulsion V, the cell points could be coupled because now we're having interactions between A and B sublattice sites, B and C sublattice sites, and C and A sublattice sites. So we could now couple the cell points, and we would have similar results to the graphene and triangular lattice. So here, some people have done the functional renormalization group. You can see that if we introduce U, there will be zero momentum instabilities. And if we introduce V, there will be finite momentum instabilities, which could be either charge or spin density waves. And it could be either side or bond order. Meanwhile, similar to graphene and triangular lattice, there could be superconductivity. And for the whole band, the cell points could be coupled already with on-site repulsion. So the phase diagram will be similar to the triangular and honeycomb lattices. So the question now is whether the Van Hove singularities are close to the Fermi level. If we look at the energy scale here, we'll see that the zero energy is actually just at the Van Hove singularity at the particle band. And this presents a hope for the correlative phase at Van Hove singularity to occur in the kagome lattice. So the question is it really like that in the realistic kagome lattice materials? So there is a new hope from a recently uncovered material in 2019, which is the kagome metal. So the kagome metal is formed with a quasi 2D structure, where we will have the A atom layers forming triangular lattice, and the vanadium atom layers which form a kagome lattice, and the antimony layers which form the honeycomb lattice. And the A atom could be potassium or rubidium or lacasium. So it has been found with an RPES that the surface Brillouin zone has this kind of hexagonal lattice band structure. And the Fermiology actually shows a proximity to the Van Hove singularity, where you can see the cell point structure here. So it turns out that if we look closer into a band structure, the Van Hove singularity occurs from the band of the vanadium kagome lattice. So indeed, it is what we have seen from the kagome lattice model. And also, the band structure shows a very strong Fermi surface nesting. That is, the Fermi surface is nearly a straight line, and it is confirmed by the band structure calculation. So this presents a hope for the correlative phase at Van Hove singularity to occur. So we can look further into the bulk and we'll see that indeed the Van Hove singularity occur near to the Fermi surface. So the question is, what are the correlative phases that were observed in the experiment? So people have found that if we are in the 3D, because we have some layer structures, the material is essentially a 3D structure, although the structure is quasi 2D because we have layer structure. So if we are looking at the bulk material with a finite thickness, we find that the superconductivity develops at like lower than 4 Kelvin, but the charge density wave can already develop at around 90 Kelvin. And you can see that if we lower the thickness, the superconductivity vanish in the 2D limit, but the charge density wave can become stronger. And people have also tried to perform the high pressure measurements. It turns out that there could be some interesting superconducting domes if we increase the pressure, where there is a new superconductivity arising, which is different from the original superconductivity. And there is an unknown high pressure phase, which has not been discussed. So the question is, what is the charge order here? So the first observation is that if we look at the charge order and if we do a magnetic field measurement, transport measurement, the material actually shows a giant anomalous Hall effect, which is at this value if we apply the magnetic field measurement. And it is similar for the A atom to be the potassium or the calcium. And it is interesting because it is the first material that realized the giant anomalous Hall effect, which is not magnetic. The previous giant anomalous Hall effect measurements were done for like the ferromagnetic materials, and this is the first non-magnetic one. Meanwhile, it was found near the end of last year that the charge order actually shows a density modulation in real space. And because some other measurements have shown the absence of the magnetic response, it is presumably a charge density wave. And if we look at the momentum scattering momentum spectrum, there are 3 peaks in the spectrum, which correspond to Q1, Q2, Q3 in between the saddle points. And we'll see that the peaks of them are different at the Q1, Q2, Q3. And a more interesting thing is that if we apply the magnetic field in different directions, the hierarchy could be like clockwise. If we apply the magnetic field in plus direction, and it will be counterclockwise in the opposite direction. It means that the density wave might be tunable under the magnetic field. So it might be, in some sense, chiral. And the density wave illustration is shown in this figure.
Sorry, I don't understand what is the clockwise and anti-clockwise meaning here.
So let's define it as if we look at the hierarchy of the height of the peak.
You mean the intensity of the peak?
Yeah.
From the lowest to the highest.
Yes.
Thank you.
Like you can see it's clockwise here, and it is counterclockwise here.
I see. Thank you.
Okay. So we should remember that this kind of time reversal symmetry breaking is unavailable from the real charge density wave. So we may want to look further about what could realize this kind of time reversal symmetry breaking. And also it has been found that at lower temperatures, there could arise some 1Q order in addition to the 3Q orders. But now the wave vector is half of the 3Q orders, and the periodicity is for lattice side. Meanwhile, there are also some additional pair-density wave proposals that were realized at the 3 half of the sail point momenta. And these results were observed only for the Cassian and the rubidium, but not for the potassium. And also, in addition to these density waves, they also found that there is a generic C-free rotation symmetry breaking, and the direction is parallel to the 1Q direction. This means that there might be some kind of pneumaticity. So a potential answer to the time reversal symmetry breaking can be realized with an imaginary charge density wave. So we have said that the imaginary CWs are the current density modulations at a finite momentum Q. And if we look at the lattice, on the lattice structure, it will correspond to a loop current. And for each loop of the currents, we could define an auxiliary magnetic flux, which could be thought of as a spontaneous magnetic field. So it corresponds to a staggered flux order. You can think of it as a d-density wave in the square lattice cuprates. But now it's for the hexagonal lattice. And the ground state of these staggered flux orders will be the 3Q orders, which is similar to the previously proposed density waves. And if we look at the flux order, there will be a 3 -1 -1 -1 structure. And similarly for the honeycomb lattice, 3 -1 -1 -1. And because there are currents in the lattice, we know that if we apply time reversal, the current direction is reversed. So it breaks the time reversal symmetry. And if we look at the band structure in the reduced Brillouin zone with half momentum scale, we find that for the triangular lattice, the Fermi surface, the Fermi level lies here, and we see that it is fully gapped. It is similarly for the honeycomb lattice, where at the Fermi level in the particle and Hove branches, the bands are fully gapped. And it means that we're having, the band structure calculation shows that we're having a Chern insulator with a finite Chern number. So the next question is, could these imaginary CWs be dominant at the Van Hove singularity? So this is actually a question which has not been well recognized before. But in 2019, Rahul and I found that under renormalization group analysis for a SUNF hexagonal lattice model, where the fermion flavor number is greater than 4, the imaginary charge density wave will be a universal leading instability at the Van Hove singularity, and it realized a quantum anomalous Hole insulator, or you can say the Chern insulator. And if we dope it away, it will go into the chiral superconductivity, which was leading for graphene. And so we could also go back to the spin flavor F is equal to 2. So we also found that the imaginary charge density waves could be degenerate with the real spin density waves under pure repulsion, which are subletting to the D-wave superconductors. So this point was not pointed out by the previous research, and we found it, although we didn't mention it in our paper. So a recent work did a more complete RG analysis for spin flavor is equal to 2 case, where they introduced some attractive scatterings among the cell points. And it turns out that with some attractive scattering, the imaginary CW could be degenerate with the real CW as the leading instability. So this poses the question that whether these imaginary charge density waves could be the answer to the unconventional CWs in the kagome metals. So to address this question, there were 4 theory papers that were posted on arXiv within 1 month to mention the imaginary CW in kagome metals. You can see that the first of them appeared in mid-March, and the last of them appeared in the mid-April, where each of them are separated by about 10 days. So today I'm going to focus on our work, which appeared in early April. So our work was that combining the density modulations observed in the experiments and the time reversal symmetry breaking, which we also observed, we combine the real and imaginary charge density waves. And we found that this kind of complex charge density waves could realize the 3Q orders, where there is a total phase condition for the complex phases, which should be quantized. We found that there could be a Haldane-model phase diagram from under a total phase condition, where we could have the trivial and Chern insulators, and also a direct point and a single-Dirac-point semimetals. And we will present the interpretation to the kagome metals. So let me now address the low energy theory of the Van Hove Fermiology. So we should remind ourselves of the hexagonal Fermi surface in the hexagonal brilliant zone. And there are cell points at the zone at the edge centers, which are related by Qs. So the first thing to notice is that we have different types of cell points. The first type is on the Hove bands, where the gamma points are lower than the cell points, which occur on the triangular lattice, the Honeycomb lattice, and the kagome lattice. And the second case is the particle band, where the gamma point has a higher energy than the cell point, which occur on the Honeycomb lattice and also the kagome lattice. So for this kind of Fermiology, we know that the Van Hove singularity occur at the cell points. So we could approximate the Fermi surface by 3 patches at the cell points. So this is a low energy theory that we're going to adopt. So we will want to introduce the charge density waves into our model. So the first thing to do is to do a symmetry analysis for the model. So the symmetry of the density waves at finite Q can be thought of as the eigenvalue problem of Q shift in the momentum space. So we could define the density wave form factors as the eigenmodes of the of TQ, where there is a complex amplitude and the form factor for the side dagger side condensate. So we have the commensurate condition is important here. So the first thing to notice that if we apply the TQ twice, it will be equivalent to T to Q. And because 2Q is just equivalent to the reciprocal lattice vector, we know that it should be a trivial operation. So the eigenvalue of the TQ should be plus or minus 1. And the eigenmodes should transform into the opposite or minus of itself when we apply the TQ. And the second thing to do is to look at the charge density wave order under TQ. So we notice that at K plus Q, the side dagger side is actually equal to, because 2Q is equal to 0, it is just psi K dagger, psi K plus Q. And it is the complex conjugate of the order at the K, because it is the complex conjugate of this one. So combining these two, we could conclude that the complex amplitude should be either plus or minus to itself when we apply a complex conjugate. That is, it should be purely real or imaginary. So so we should identify the symmetry channels of where the density modulations are realized by the purely real and imaginary orders. So for the real orders, we have the S-wave order, where the form factor is uniform in the brilliant zone. And another real order is the D-wave order, where if we go around the Fermi surface, it will change sign once, twice, 3 times, 4 times around the Fermi surface. And the real orders will correspond to a side or bond orders. Meanwhile, if we look at the imaginary order, it will be a current order. And the order, if we look at a form factor, it will change sign for once, twice, 3 times, and 4 times when we go around the Fermi surface. So it is a D wave. So the next thing to do is to analyze the interplay between them. So we look at the order parameter at the 3 momenta, 1, 2, 3. And we because we're combining the real and the imaginary orders, we could define it as a magnitude and the complex phase. So we could derive a Ginzburg-Landau free energy, where we have quadratic order and quartic order, and the cubic order. And by looking at the quadratic, if the quadratic order turns negative, there could be the development of the order parameter, which corresponds to the formation of charge density waves. And the free energy minimization to distinguish the ground states is done by identifying the anisotropies. So the first anisotropies to look at are the red ones. We can see that the 3Q orders are energetically favored. That is, if we have a finite magnitude for the order parameter vector delta, we should have delta 1, delta 2, delta 3 to be equal, so that we could maximize this term. And also at the quartic order, because this one is negative, to minimize this term, we should have them to be equal to each other. And to further break the degeneracy, we could look at the blue ones. So if we look at the whole band, the prefactor here is positive. So we will want to have cosine to be -1. And this imposes a total phase condition. Meanwhile, for the particle band, the prefactor here is negative. So we want to have cosine to be +1, which imposes another total phase condition. So the third degeneracy breaking term is the secondary term here. So this term, as you can see, it couples only the real orders. So it will favor the real orders. However, this term is coupled in addition to the, besides the cell point, it is also coupled to the gamma point, which is away from the Fermi surface. So at low energy, we know that it should be a secondary term compared to the other ones with only the cell points. So we should now understand what are the ground states in terms of the free energy minimization. Yes?
May I ask a question? So maybe, so how to derive the free energy here? What was the principle?
So that's a good question. So we could first look at the patch model here, which gives us a non-interacting Hamiltonian with the low energy cell point dispersion energy. Then we could introduce the order parameter here. And you can think of it as solving as an interacting theory. And you can do it by a path integral to derive the partition function. And with the Hubbard-Stratonovich transformation, you can derive the free energy in terms of the order parameter. Does it answer your question?
Yeah, so okay, the calculation is kind of complicated. You using maybe the renormalization group?
Actually, you don't really have to do the renormalization.
Okay.
You can think of it as first we derive the free energy of the theory, of the interacting theory. Then we integrate all the fermion modes with some finite condensate of the side bilinear.
Oh, okay. Let's just using the bilinears.
Yeah. I assume the bilinears. So you can think of it as some effective quadratic Hamiltonian.
It's semi-classical.
Yeah, semi-classical statistical theory. Okay.
And maybe another question is why doesn't the form factor enter F here?
Yeah, so the form factor indeed enters the calculation. So that's also why we have this kind of anisotropies here.
Oh, okay. It's just hidden here. I mean,
yeah. It might be too complicated to show them here, so I just jump over them.
Okay. Thank you.
You can look into our preprint to see the equations.
Okay. Yeah. Thanks.
I have a quick question. So about the procedure to minimize the free energy. So I should think of it as some kind of self-consistency ansatz, but in principle, you don't need to use that ansatz, right?
Can you explain it further?
Like, once you get the Ginzburg-Landau free energy based on the order parameter you assumed, in principle, you could have something that breaks the symmetry at the very beginning for your
Yeah,
ansatz.
that's
So
true.
will that give you something that have even lower energy? Because I think the Ginzburg-Landau free energy argument seems to be, if I find an ansatz, then I need to compare the different ansatz and which one has the lower energy, lower free energy. And this free energy seems to be quite complicated. So my question is, did you try other orders, or that's the ansatz that you think it should work?
Yeah, that's a good question. So the thing is that although it is complicated, we could try to do it step by step. For example, we could try to find out the conditions that are consistent for all of the anisotropies, and usually it will be equivalent to deriving it with an exact like numerical computation.
Mm-hmm.
Right. Yeah, it has been demonstrated to be true for like the spin density waves on the at the Van 't Hoff singularity, and also for each case of the, real and imaginary orders.
Yeah, but my question is, like, suppose I set delta 3 equal to 0, can I get, is it going to be something that's physical?
Actually, if we set delta 3 to be 0, we will have all the anisotropies to be, we'll only have the anisotropy finite here, for example. But this term cannot be stronger, for example, than this term. And also, even if we don't have the qubit terms, it will still be smaller. It will still have a higher free energy than we have all of them to be finite.
I see.
This could be confirmed by some inequality theorem.
I see.
Yeah, like if you have 1 over square root 2 for it and 1 over square root 2 for it, it will be smaller than having all of them to be 1 over square root 3.
I see. I see. Okay.
Yeah. Is it satisfactory for you?
Yeah, I think so, because I'm just curious about like the procedure, because usually the minimization of Ginzburg-Landau doesn't have this nice property that you can see that directly.
Yeah.
So I'm just wonder, like,
Yeah, that's true.
Is it just by luck, or there are some good arguments that we will get that, and the procedure exhausts all the possibility?
So I think one could think of it as, if we look at the for example, the patch model, the free energy is clean in terms of the C3 symmetry, or the symmetries of the density waves. So each of the anisotropy will be equivalent to some kind of irreducible representations for the symmetry.
Yeah, my question is, what if C3 is broken? That's basically my question. Maybe C3 broken
Yeah,
is going to give
that's
you
a
even
good
lower
question.
energy.
In that case, one has to really do it exactly.
I see.
Yeah, that's the good question. But here, it is a clean model, so we could just do it by eyes.
I see. Okay.
Although indeed, a numerical confirmation may also be important.
I see.
So we could now try to look further into the degeneracy breakdown under the favor of real order. We could see that if we look at if we impose phi 1 and phi 2 and set phi 3 to obey the total phase condition, we find that the free energy has the minimum at the corners, where phi 1, phi 2, and phi 3 are either 0 or pi. It means that the real orders are indeed favored, under the total phase condition. So we should also characterize the strength of the real order in the phase diagram. So we can see that at the corners, the strength of the real order will have the maximum 1, which correspond to the purely real orders. And if we go to the bulk of the phase diagram, the imaginary orders start to emerge. In this case, the strength of the real order will decrease. So we could define an upper bound for the strength so that we could constrain the available regime of, in terms of the real order strength. So the first case is that when the real and imaginary orders are balanced, that is, for example, when they have the same critical temperature, the maximal real order strength we could have is 1. That is, we could have a purely real order. And if we look at the whole phase diagram, we know that the free energy minimum occurs at the real order, so it is the ground state. If we have a stronger real order, for example, the critical temperature to be higher than the imaginary one, the upper bound is still 1. So again, we have the favor of real order. However, if we have a stronger imaginary order, which is our focus, for example, we could have the critical temperature of it to be stronger than the real order, then the maximal real order strength we could have would now be smaller than 1. In this case, we are pushed into the bulk of the phase diagram, or you can say we are pushed into the higher free energy regimes. And although the functional forms of the two diagrams might be different, the contours with equal real order strength will have the same energy. That is, the contours in the two diagrams will be the same. So we could characterize the degenerate ground state at each real order strength by the energy contour in the free energy phase diagram. So if we are pushed further so that the upper bound is lower than the minimum of the real order strength here, which are the red dots, we are breaking the total phase condition because it is not compatible to the total phase condition now. And if it becomes lower, we will evolve continuously to the purely imaginary order, where the delta R upper bound will vanish at the end. So this is the phase diagram that we're going to look at. So I'll show next that we have a Haldane-model phase diagram here. So to look at the density width, we need to first look at the reduced Brillouin zone. So we have to fold the bands in the original Brillouin zone into the half times half reduced Brillouin zone. And we see that we have 3 Fermi lines at the Fermi level, which cross at the gamma point. And indeed, if we look at the band structure along the gamma n lines, there will be a flat line. And we have some nodal points at the endpoints. And an important point is that if we look at the gamma point, there are some positive energy and negative energy regimes around it. So it is because the gamma point dispersion energy are inherited from the original cell point. So they are D wave. And this kind of topological D wave quadratic band crossing are non-trivial because they will have 2-pi phase winding when we go around them. And this is protected by both C6 and time reversal symmetries. So we will show that the density width can gap out the quadratic band crossing and induce some topological nature. So the first order we consider is the real order. We can see that if we introduce the 3Q real order, it gaps out the whole Fermi surface, as you can see from the band structure. And there could be some side or bound orders, as you can see from the triangular and honeycomb lattices, and from the kagome whole band and the kagome conical band. And because we have both C6 and time reversal symmetries, the quadratic band crossings are protected. Meanwhile, if we look at the density orders, we will have the 3 -1, -1, -1 orders, where we can also see it if we look at the triangle density, which is calculated by summing the side and bond densities around it. And the particular thing to notice is that the Hove and particle bands have different patterns because the sublattice structures are different. If we look at the Hove band, we have the side plus bond orders. And if we look at the particle band, we only have the bond orders. The next thing to look at is the 3Q imaginary order. We see that at the Fermi level, the band structure is fully gapped. And as we have said previously, it is a Chern insulator. And you can see that on the lattices, there are some current orders. So because it breaks the time reversal symmetry, the quadratic band crossing here is gapped. Meanwhile, we should notice that the physical orders for the imaginary orders are the current orders because they are the expectation values that we're really evaluating. But we can imagine some kind of flux orders which penetrate the triangle or the hexagons. And these fluxes are auxiliary, which are imagined to match the physical currents on the bonds. So we have a degree of freedom to choose the flux order. The first choice is the staggered flux order, where we have the 3 -1, -1, -1 order. Meanwhile, we could also choose another kind of order, where we have penetration of flux only on the triangles, with all of the 3 edges being current induced. In this case, we have a 1000 flux order, and this kind of dilute magnetic field order could indicate clearly the time reversal symmetry breaking. That is, you can think of it as a Chern insulator induced by some dilute spontaneous magnetic field. And it is a kind of quantum anomalous Hall effect. So we could understand further about the formation of the Chern insulator. First, if we introduce the 1Q order, it will break the time reversal and the C6 symmetry. So we will gap out the quadratic band crossing. And the Fermi level will now become a null point and some nodal curves. Here we will have an effective time reversal symmetry, which is realized by combining a one-side translation where the current along this direction goes to here, and by applying a time reversal so that the current direction is reversed. Meanwhile, we could have an effective inversion where we again apply a translation and with an inversion with respect to the bond so that it also reverses the current order. If we introduce another Q, it will gap out the nodal curve. So now there are 2 Dirac points here, and equivalently here and here. And these nodal points have the plus or minus pi phase winding, from which are inherited from the plus or minus 2 pi quadratic band crossing. We still have the effective time reversal symmetry and also the effective inversion symmetry. But if we introduce the third if we introduce the third order, we no longer have this kind of one-side translation. So the effective time reversal symmetry is broken, and we gap out the Dirac point. So in this case, if we gap out the Dirac point by breaking the time reversal, as we saw previously, we are having the Chern insulator as in the Haldane-model. And this is the origin of the Chern insulator from the 3Q imaginary order. So because we have different kinds of gapped faces, we should also have some gapless faces in between. So the first kind is the direct semimetal, where you can see that if we introduce some kind of orders, there could be 2 Dirac points in the band structures, equivalently at least 2 points. And on the lattice, we will have some side and current orders. So the symmetries here are as follows. First, we will have an effective time reversal. That is, if we apply a one-side translation upwards, we translate this bond to here, equivalently here, and apply a time reversal so that the current direction is reversed. We will return to the original pattern, so it is symmetric. Similarly, if we could apply an effective inversion, that is, we again translate the lattice in one side and equivalently here, and apply an inversion with respect to the bond center to inverse the current direction, and it will be invariant under this kind of transformation. So combining these two symmetries, they will protect the Dirac points at these 2 points. Meanwhile, if we don't have this kind of symmetries, for example, if we apply a one-side translation from here to here, the side densities are different. We no longer have this kind of symmetries. So if the T and P are both broken, there is no symmetry between plus and minus K. In this case, there is no fermion doubling theory. And we will only have one Dirac point in the Brillouin zone here. And this one will be gapped here. So combining all of these phases, we will have a Haldane-model phase diagram. We're starting from the corners with real order. We have the trivial insulator. And when we go across some phase boundary, we will go into some Chern insulators, which are continuously connected to the 3Q imaginary orders. And along the phase boundaries, at the corners where the effective T and P are present, there are direct semimetals. And away from them, where both symmetries are broken, we have the single-Dirac-point semimetal. So this summarizes the complex charge density waves. The final question is, are they relevant for the kagome metals? So the first experiment we're going to compare with is the chiral charge order. So we see that the scattering momentum have different peaks in terms of the density modulation wave factor. So in our theory, we could think of them as the different magnitudes of real order. That is, we can think of it as a 3Q complex order with different phases along the 3 momenta. So if we choose the according phases to the experimentally observed peak heights, we find this kind of pattern. And you can see that the warm colors indicate that the bond order are positive, and the cold colors indicate that the bond orders are lower. And you can see that around this hexagon, we have this kind of star that is like this, and here, and here. And this is called the Star of David pattern. And we can compare our pattern to the pattern here. You can see it like lowest and highest, lower, lower, and lowest, higher, lower, lower, and the Star of David pattern. And we confirm that if we choose the phases accordingly, under a total phase condition, it occurs in the Chern insulator phase, so it could induce some kind of anomalous Hove effect. We could also compare our result to the lower temperature symmetry breaking. First, if we choose the according phases, we found a band structure here, and we find that at the M3 point, it has the smallest gap between the valence and the conduction bands. So if there are some additional interactions, maybe there could be some secondary pneumaticity along this direction. So this is along the 1Q direction. So indeed, it corresponds to the rotation symmetry breaking along this direction. Meanwhile, the other values may be able to develop a 1Q charge density wave. And because the momenta difference between these two values are equivalent to M3 prime, it could correspond to the 1Q order here. So maybe this is just the 1Q order. And this kind of value theories may also support the pair density waves at the 3-half cell point momenta. It has also recently been observed that the CW gaps are indeed momentum dependent. And we can look at the gap structure in the reduced Brillouin zone here, centered at the endpoints. So near the gamma point in the original Brillouin zone, it seems to the charge density wave seems to be gapless, and because the Fermi surface around here occur from the other larger lattices than the vanadium kagome lattice, it may also just mean that the charge density wave only develop on the vanadium kagome lattice. And from the gap opening at the endpoints, we find the evidence of the charge density wave at the Van Hove singularity. So we also observe some kind of gap closing or nearly gap closing at the end prime points at the edge center of the reduced Brillouin zone. And it may indicate that it might be related to the non-perfect nesting, where we could have some Fermi surfaces around the valleys at the endpoints and prime points, so that if we have charge density wave, it will be gapless. It may also have similar effect if we have finite doping away from the Van Hove singularity. And this kind of effect, that is the presence of some Fermi surface, may lead to some giant anomalous Hole effect, which are not quantized. So here is the summary to my talk here. So we analyzed in the play between the real and imaginary charge density waves, where the complex charge density wave manifests a 3Q order under a total phase condition. And we find the Haldane-model phase diagram for the complex charge density wave. And we also present an interpretation to the kagome metals. And here are some outlook to our work here. First, we may try to further confirm the evidence for the current orders, for example, in the experiments. And we may try to match it with lower temperature symmetry breaking. And it has also been proposed that in the recent theory work that the 3D effects might be relevant from the interlayer coupling. That is, we may be able to couple the CW orders between different vanadium layers. And our interpretation is that it might be able to pin a particular ground state in the degenerate energy contour as we saw from the free energy minimization. And we may try to analyze the interplay between the CWs with the superconductivity, which may have a significant effect on the pressure or the variation with the thickness. And with all of this, I would like to thank you for your focus and the listening. Thank you very much. And sorry for the overtime.
Thanks. Okay, so are there questions?
Maybe I can ask some. Yeah. So thank you for the talk. Yeah, I want to know more about how your theory related to the experiments, because according to experiments, it has a finite thickness, right? So maybe if finite thickness, so maybe if you including 5 or 6 layers, the band structure completely different. There's no Van Hove singularity. It's maybe one possibility, right? So how do you justify from that point of view?
So that's a good question. So actually, this question has somehow been answered to a certain level by this work. So they propose that because the kagome metals have quasi-2D structure, so that if we look at the band structure, let me try to go back to. If we look at the lattice structure here, the potassium layers are nearly decoupled from the vanadium and the antimony layers. This means that the layers between between this vanadium plus antimony layer may also be nearly decoupled from the other layer. So the relevant charge density wave might be the charge density wave that develop in the 2D structure. And to address the 3D effect, it might be addressed by thinking about the secondary coupling between the charge density waves of different layers.
So experimentally measure a large anomalous hole conductivity, right? It's not quantized to, or it should proportional to the thickness, right? In terms of your model, layer will count one quantized hole conductivity. So
yeah, that's true.
So maybe there's a way to
confirm this.
Yeah, something like that.
Yeah, that's a good point. I think they haven't really compared it in different thickness, so that might be a good generalization from current result.
Okay.
Yeah, thank you for that good point.
Can I ask a question since you are at this point? So in this slides, is this density like the upper right part? There's a color density plot for electron density. Is it measured by experiment or?
So so this one is from RPES.
I see.
And this one is from first principle calculation.
Wait, usually can RPES see the charge density directly, or they need to do some manipulation? Because I think usually RPES you just see the bands. Like
yeah, but I think they can see the Fermi surface.
I see. So in principle, if they can do RPES, does that mean they can also do some kind of STM to see this real space pattern?
Yeah.
And then maybe not in the momentum space, but
yeah, like I think this one was obtained from STM.
So it's a real experiment.
Yeah.
I see. Interesting. So my question is like, if it is a nice surface, then probably one can do some kind of did people try to put some impurities and see some kind of Fidel oscillations? Because I think at some point when people try to use STM to detect TIs, they have tried to use that kind of thinking.
You mean some kind of finger point for the topology?
Yeah, like yeah. My question is because this underlying CDW is some kind of special order. I wonder whether when the impurity is nearby, whether there are some signature that your theory can predict. Then maybe it will be an interesting prediction that people can try to measure or something.
Yeah, that's a good point. I think people have not done it before, and if from our theory we have a topological response, so it might be possible.
Mm-hmm.
Right, but I don't know what could be there, and maybe further calculation is needed.
I see. Mm-hmm. Also, another quick question is from the material side. So you focus on most of the data is for the vanadium type compound, right? So did they try to do, change some chemical, like changes to some other transition metal ions? Like, I don't know, vanadium is kind of tricky because I think the valence is special. Like maybe magnesium or some other things.
I think they haven't done it. There are some other kinds of kagome metals, but I think they are not of this type. Yeah. But currently for this kind of kagome metal with Van Hove singularity at Fermi surface, they have only done it with vanadium.
I see. Interesting. Okay.
That's a good generalization direction.
Okay.
I have one question. Actually,
Yeah.
you mentioned that this material is a kind of layer compound.
Mhm.
So basically, you can assign them as a 2D material. Is this correct?
It's like a
In the
flat
sense,
material.
yes.
But
Uh,
yeah. Go ahead.
in the experiment, you can prepare by the in situ cleavage or something.
In the experiment, they prepare it as a nearly 2D material. That is, you have some 2D plane, but with a finite thickness.
Mm-hmm.
And the quasi 2D structure is because in the material, it is a layer structure, and each layer is nearly decoupled. That's why they refer to it as a quasi 2D structure.
Okay.
Yeah, and indeed,
Yeah.
one has to find. I mean, this kind of physics may only be found when we have a thin enough material, but it
Okay.
cannot. Yeah, you can see the thickness dependence here.
Uh-huh.
So usually they do it in 100 nanometer.
You mean the thickness?
Yeah.
Okay. So can you go back to your slide of page 8?
8.
Yes. I remember you show, yes, the density of state as function of energy for the graphene, right?
Yeah.
You can see this distribution of the density of state. It's very much like the D-wave superconductor. But
Right.
do you have any idea in experiment people can measure such kind of density of state on the graphene? For example, you can, I know this is for the freestanding graphene, right? This calculation.
Right.
But basically, you can have the sample like this HOPG. It's a layer of the graphene, and basically the coupling between the layers are very weak. So you also can treat it as a freestanding graphene,
Right.
staking layer by layer. But from the literature, do you have any idea what kind of experiment can show such kind of density as a function of energy?
So that's a very good question because, as you have mentioned, I think it's somehow equivalent to the question that it is hard to really dope it into finite doping regime. But I think recently people have found that if we do it with an intercalation, one can indeed achieve the finite chemical potential regimes. But now the density of states may not be logarithmic divergent. Instead, it will be power law divergent, which realizes a higher order than Hove singularity. And that's another story. But I think they have, a definite point is that they show the intercalation to be an answer to the doping to finite chemical potential.
Okay. The doping means you go the single layer graphene on the substrate, and then you dope with the electron or hole. Then you can.
I think it's more like we intercalate some other atoms into the graphene.
Okay.
Yeah, and to achieve the effectively, it is like the electron density is higher than charge neutrality. Yeah.
So you mean like putting potassium or something on the graphene?
Yeah, something like that.
Okay. Yeah. Thank you very much.
Thank you. Yeah, that's a good point because it has been known that it is hard to really go into this regime.
Sorry, I also one short question came into my mind. From the upper measurement on this vanadium antimony compound, you just show at page 13. Yeah, sorry, 12. This one. Page 12.
Okay.
The upper measurement. Since you have the charge density wave in this system, do you see any nesting behavior, the electron hole pocket nesting behavior, or the charge density wave reported in this kagome material? It's from completely different origin.
Sorry, could you explain your question again?
Typically, the charge density wave comes from the nesting behavior on the Fermi surface, especially right. You have a nesting vector connecting the electron and hole pocket.
Right.
Do you see this in this material?
So yeah, so so we see that we have this kind of Fermi surface here, and we can see that the K points will be below the Fermi surface, and the center region will be higher than the Fermi surface in terms of energy.
Okay.
Yeah, so for example, we are having the hole pocket here and here near the Fermi surface. That is, let me try to explain it with another plot. This one. So as you can see, we have opposite energies. If we have a finite momentum difference between the points. And I think this is the electron and hole pockets that you're referring to.
So you do have the nesting Q at this kind of Fermi surface.
Yeah.
Okay.
Yeah. I think in the real material, they are not really perfectly nesting, but the nesting degree is strong enough so that there could be a charge density wave.
Okay, thank you very much.
Thank you.
So I think do we have more questions?